we say? So we said that we're going to, it's based on coordinates of what? Rotating an angle counterclockwise from 3 o'clock. And after we do that, so say like here's the angle 2 pi over 3. And that angle, so the angle 2 pi over 3 corresponds to pointing in this direction out from the pole. And so then that direction, so that's the angle theta equals 2 pi over 3. So then this is the direction of positive r. Positive r is extending this way. So r equals 1, 2, 3, 4. And then negative r would be exactly in the opposite direction from this direction of theta equals 2 pi over 3. So negative r then would project back this way. Here would be negative 2, negative 3, negative 4, corresponding to the angle 2 pi over 3. Remember that? Okay, so that's just, and then we said that given any point, which we write as r theta. So theta really comes first, but when you write the convention is to write r first. I don't know why, that's kind of backwards, but that's the way it is. Because really you sweep the angle, and then your distance from the pole is like a function of the angle measure. But for some reason they chose to do it, write it this way, r comma theta. Y is a function of x, right? And so then to write the x and y coordinates of this point, we said, well, we can think of this, so this is r is like a hypotenuse of a triangle, and so the x coordinate would be this leg of the triangle, which we define by r cosine theta, and then the height of the triangle would be our r sine theta. Okay, and then one thing we didn't mention, which we'll mention quickly here, is if you had x and y and you wanted r and theta, so this is, you have r and theta and you want x and y, that's this, that's these two. If you have x and y, how would you, so for instance, you have that leg x, the length of that leg, you have the length of this leg y, how would you find r? What would r be? Yeah, so it'd just be the Pythagorean theorem, right? Because x and y would be your two legs of your triangle that you would have, and then your hypotenuse would be r, so it would be square root of x squared plus y squared, which comes from, so oftentimes when you're using this, you'll just use r squared equals x squared plus y squared. You won't use square root for r, you'll actually use this as well. You'll see this come up a lot. R squared is x squared plus y squared. Okay, and then what would theta be? So again, we got this triangle here. So this is the angle theta, and this is r, and this, we have x and y. What would theta be given x and y? So x and y, what form? The opposite and adjacent side of that triangle. And so which trig ratio is that? Opposite and adjacent. So tangent theta is y over x, so theta would be arctangent of, but this will only give angles, arctangent will only spit out angles between negative pi over 2 and pi over 2. So you might have to adjust depending on your point, where your point is and what kind of angle you want. So okay, so that's only going to give an angle between negative pi over 2 and pi over 2. So you have to reconcile that with where your point is, and you're going to maybe use that angle to then find the actual angle theta, which is swept counterclockwise from 3 o'clock. Okay, so that's given r and theta. We know how to find x and y. Given x and y, that's how you find r and theta. Okay, now so these relationships for polar coordinates, they're always true. No matter which, if you've got a polar function, it's still, x is still equal to r cosine theta, and y is still equal to r sine theta. Okay, so these are important. And always true in the polar context. Okay, and so we were working on, that's kind of a review. warm up. We were working on r, so this function of theta, r is a function of theta, where it was 2 sine theta, right? So we had this right here, r equals 2 sine theta, and this is where we finished off last time. And we said to do this, we're going to sketch it like in rectangular coordinates, and we're going to use that graph to help us sketch the polar graph. So we said 2 sine theta looks like this. It starts at the midline, heads up to 2, back to the midline, down to -2, and back to the midline. And so then we went quadrant by quadrant. We said from 0 to pi over 2, what does r do? From 0 to pi over 2, how does r change? From 0 to 2. So watch, as I increase that angle, you can watch that r value still increasing from 0 to 2. But because that terminal side of the angle is turning, it's 0 to 2 doesn't just go straight out, right? So it's going out as you're turning, right? So it's extending out away from the pole from 0 to 2 as that angle is rotating. So that caused this arc to form, right? So this is r extending from 0 to 2 as the angle changes from 0 to 2 pi. And then what's next? As we go from pi over 2 to pi, what happens to r, according to our graph there? So we're looking up here. As we go from pi over 2 to pi, the value of r goes from 2 to 0. So, and that's like symmetric. You can see the symmetry there. So it's going to head back to 0, kind of the same way that it went out to 2. But now that's going to happen as we rotate from pi over 2 to pi. So if we trace that out. So watch the r value. You see it's decreasing starting at 2. Now it's coming in on the ray until it's 0 at pi. Okay, and so then we have to deal with negatives, right? So from pi to 3 pi over 2, this third quadrant, what is the value of r? It's negative, 0 to -2. So that's actually going to plot where? Up in the first quadrant. Do you see that? So as I traverse from pi to 3 pi over 2, as the angle changes, all my r values are negative, so they're in the opposite direction out on that red ray, right? On that red ray. And it actually just recreates what we already did in the first quadrant. And then the last, from 3 pi over 2 to 2 pi, we're going to go from -2. So here we are at 3 pi over 2. Where is -2? So this is the positive direction. 3 pi over 2, this is positive direction of r. So negative direction is here, so here's -2 at 3 pi over 2 is up here. And so then as we go from 3 pi over 2 to 2 pi, the r value is going to go from -2 to 0. And so that'll actually plot over in the second quadrant. Even though our angle is pointing in the fourth quadrant, r's are negative, so that's plotting over in the second quadrant. And again, it just recreates what we already did. So you get this whole arc. Maybe it's a circle. We're thinking maybe it's a circle. We get the whole thing in just from 0 to pi. Not necessarily. So the key is that sometimes the period of the polar graph will be the same as the period of the rectangular graph. Sometimes it'll be different. So there's no really rule. You just have to do them all separately and keep drawing the polar graph until it starts to repeat itself. All right, so that may be a whole period of the rectangular. It may be 2 periods of the rectangular graph. It may be half a period, like this one. Okay, so you just have to keep drawing the polar graph until it starts to repeat, and then you know you're done. Okay, so we were going to confirm that this is a circle. So how do we confirm this is a circle? Well, it comes back to this here. So to do that, we know our circle equation in rectangular coordinates. So can we change this from r and theta to an equation of x and y? So can we use our relationships between x, y, r, and theta to rewrite this as an equation of x and y? So let's look at this, the right-hand side, 2 sine theta. Does that equal anything? Does it equal x or y or anything like that? No, I'm looking at the 2 sine theta. So if I would just want to focus on this right-hand side, 2 sine theta. Does it equal anything with x's and y's? It would be nice if there was what? We're trying to get this to look like an x or a y. No, not squared. Remember, I put a star by it. X equals our cosine theta, and y equals our sine theta. So I'm looking at that right-hand side and saying, boy, it sure would be nice if I had a r, because then this right-hand side would be 2y. Do you see? But I can't just multiply it by r. But I could multiply both sides by r. You see what happened? So look, I'm trying to get this to look like y, because I know y is sine r sine theta. Let me actually just leave the original up here. And then I'm going to do what? I want, if I had 2r sine theta, then that would be nice, because it would be equal to 2y. All right, but I can't just include an r over here, but I have an equation. So multiply by r over here, and multiply by over here, I get. And what is r squared? X squared plus y squared. Right, by the Pythagorean Theorem, thinking of that right triangle. So look, we just got an equivalent equation to r equals 2 sine theta. X squared plus y squared equals 2y is equivalent to r equals 2 sine theta. And we're back in rectangular coordinates. And so then we can say, oh, we know what the equation of a circle is. Maybe we can start moving towards that. So what is the equation of a circle? X minus a squared plus y minus b squared equals r squared. Everyone remembers that? And AB is the center, and r is the radius. So this is not polar r. This is just the length of the radius of your circle. So if we can make this look like this, then we've got a circle. So what do we need to do? So what do we have? We have a perfect square here, y minus b squared. So what do I need to do? I need to complete the square, right? Complete the square. So x squared is fine as it is, because that's like x minus 0 squared. It's fine. So how do I complete the square? Remember how to do that? A perfect square trinomial. Yeah, so you take the coefficient of the linear term, you divide it by 2, and you square it. Is that familiar? So negative 2 divided by 2 is negative 1, squared is 1. So I'm going to add 1, and that will make it a perfect square trinomial. But if I add 1 to this side, I got to add 1 to this side. It was 0 before. Add 1, and I get 1. So what am I trying to do? I'm trying to make this equation look like this one. That means I need a perfect square on my y's. I already got it with x minus 0. So to get the perfect square, you take that linear term, divide by 2 and square it, and that's what you add. So we divided negative 2 by 2, which was negative 1. We squared it, we got 1. And so I'm going to add it here, and I'm going to add it here. And so then what is that? Y minus what squared? I mean, that's easy, right? So it's y minus 1 quantity squared equals 1. Do I have a circle? Center is 0, 1, radius. Does that agree with the circle that we have? Center at 0, 1. This is 2, right? So radius is 1. It does. So indeed, that thing that we sketched is a circle, and we just proved it mathematically. Questions on that? So lots going on here. We're sketching. We're using our relationships between x and y and r and theta then to figure out what we've got in the end. In this particular case, it turned out to be a circle. Okay, so we're gonna practice sketching. The next one we want to do is. Oh, did my notes end up in the stack? Yeah, that's not it. It's my fault if it did, but I don't think it did. Anyway, so we want to do cosine theta plus 1. So we want to sketch cosine theta plus 1. You've got some blank axes there to use. So the function r equals cosine theta plus 1. How are we going to start doing this? What's that? Yeah, so we need to know how to sketch cosine theta plus 1 in rectangular coordinates, then we're going to use that graph to help us sketch the polar graph. So can you sketch that in rectangular coordinates first? So things we ask are, so midline, it's a good place to start, midline, and then from that, the max and the min. What's the period? And then we're gonna divide it up into 4 intervals. It's okay, I think I remember. I don't know what to do. And then we decide. It is. You're right. I didn't recognize the back of that. And then we're gonna sketch. So is it plus or minus, sine or cosine for the sketch? So this is kind of just a real. That's a real skeletal kind of strategy for sketching these. And then once you have the sketch of rectangular coordinates, then you want to take it a little section at a time and let the angle increase and look at the graph, look at what r is doing, and then you're going to sketch that in the polar graph. So you think of the angle rotating, and then as it rotates, r is going to change according to your rectangular graph. So I'll give you a second to see it, how you fare at this, and then we'll do it together. no calculator exercise. What do I want right now? No, because it's not anything you should recognize. So that was just to confirm that that one was a circle. I don't know if you can. Can you? Yeah, you could come up with something pretty easily. Yeah. Oh, shoot. Okay, so this is really exactly the same. It's just blown up by 2. Okay, so it's exactly what you would get. It's just magnified by 2 out from the pole. Okay, because everything's multiplied by 2. So what would our midline be? So can you make a quick adjustment here? So what would it's going to make it for easier graphing too, to make it bigger on those little axes. So what is the midline of this? 2, right? You should have had a midline of 1, right? You should have had a midline of 1. This one has a midline of 2. And then max and min will go between 4 and 0. You should have had 2 and 0. You should have 2 and 0. So it's 4 and 0. And then what's the period? Same period as yours. 2 pi. And to sketch this, we're going to chop that up into 4 pieces. So that'll be our standard pi over 2, pi, 3 pi over 2, 2 pi. And we can mark those off on the midline. And then left is just to know what cosine is. So at the start of the cosine period, are we at the midline, or max? Max. And then in the first quarter period, we go to the midline. Next quarter period, it's on the min. So it's exactly what you should look like, except being from 0 to 2 rather than 0 to 4. It's really the exact same problem, just scaled by 2. Are we good with that? Okay, so then where are we going to start here? We're going to start at when theta is 0. What do we have? You should have had 2. Okay, but I have 4. Okay, so mine's just going to be twice as big. And you could, if you want to do this one, 2 plus 2 cosine theta on the next little polar graph there on your sheet, that would be good. We're going to come back to this one and do some other math on this one later. So what happens in the first quadrant? So as theta, imagine theta changing from 0 to pi over 2. What does the distance from the pole do as we rotate from 0 to pi over 2? Decreases to 2. Or in with the one you worked on, what should have been 1, but same idea. So we imagine as we're rotating what? That as that terminal side rotates from 0 to pi over 2, that r is decreasing from 0 to 2. So here's what that looks like. Watch. Watch the point on the ray. Ready? Oh, jeez. And I need 2. Okay, here we go. So watch the point. As angle increases, notice it's coming in, decreasing. And notice, look, it's because it hasn't gotten to 2 yet. When the angle gets close to pi over 2, it's further than 2, right? It's not gonna. So a common mistake students would make is they would kind of draw it like this, and then it comes in like this. But when your angle gets close here, it's greater than 2. So it's going to be out further from 2 because it's decreasing from, the radius is decreasing from 4 to 2. Do you see that? So look how far out above 2 it is there. But then when it reaches pi over 2, it makes it to 2. So again, as the angle increases, that distance from the pole is decreasing from 4 to 2. What does that look like? As we go from 0 to pi over 2, the radius decreases to 2. Okay, then what happens from pi over 2 to pi? From pi over 2 to pi, as that terminal side bends down to the x-axis, what happens to our radius? So we look at the graph for that, right? We come over here and we look. Say, oh, the radius goes from 2 to what? 0, or what you sketched originally from 1 to 0. So what's that going to look like? As we turn that angle, that radius is going to pull in until when we're at pi, the r is 0. That's at the pole. So what does that look like? Can you imagine that? Okay, and then what? So then we get to pi, and what happens? In the next quadrant, from 3 pi to 3 pi over 2, as that angle increases, what does the r do? From 0 to 2. Yeah, it kind of does. From 0 to 2, right? And you can see it's kind of symmetric to what we just did. Now it's going to, this went down from 2 to 0. This going back out to 0 to 2, so that at 3 pi over 2, we'll be at positive 2 right here, right? So it's going to be like I said, symmetric to what we just did, but now increasing out from 0 to 2. It's just impossible to do it. All right, last quadrant from 3 pi over 2. So as we go from 3 pi over 2 to 2 pi, r goes from what? R goes from 2 to 4. So now as we rotate through this angle, or rotate through this quadrant, r is going to increase. Starting at 2, it's going to increase out to 4. So for this one, the period of the polar graph is the same as the period of the rectangular graph, because now it's going to start over. Forgot what this is called. Is it a limicon? Or cardioid. Limicon has the loop inside. Is that right? Okay. Cardioid, right? Cardioid, because it looks kind of like a heart. Right? This is? Ah. So what is a cardioid? You don't have to know the names for the test. Yeah, so this.
It's special because you can get it by rolling a circle around another circle.
Which one? So limicon is a specific type of cardioid? Is that?
Seems so.
Okay.
It might be equivalent.
Not all of them.
The cardioid is a special case.
Yeah, I'm really struggling with spelling here. Oh, it's I-O-I-D.
IOID.
Okay. Questions on this example? And like I said, we'll come back after we do one more. We'll come back and we'll do some calculus on this. So the next one we want to do is 3 times sine of 2 theta. You're on your own. Show. You will have to do this for the final without a calculator. This is really understanding polar coordinates really well. This one's harder. Gotta get that rectangular graph right. You want to check the rectangular graph? Does that make sense? Because the period of sine is 2 pi, so we're thinking about this reaching 2 pi. Okay, so then what does theta reach in order for 2 theta to reach 2 pi? Yeah, so what is theta? Right, so when theta hits pi, that's going to be a period because this is going to get to 2 pi and the sine will start over. So that's your period. Want the whole polar graph? No, I always want the whole polar graph.
All three sides of pies are necessary. As long as it's close, right? I mean, I don't see you getting your protractor out. I spent many minutes. Oh, that's decent though. Actually, this one's kind of clean though.
Okay, so this is the. You should have gotten. Did you get the rectangular graph? So the 2 theta, what does that do? Well, it affects the period, right? So what does the argument of sine need to reach to get a whole period? To start over with sine. 2 pi, right? So whatever you put into sine, when that reaches 2 pi, sine starts over because that's the period of sine. So, but we need the period in terms of theta. So therefore, when 2 theta reaches 2 pi, this is going to start over. When 2 theta reaches 2 pi, because it's a sine curve, it's going to start over. That means when theta reaches pi, this thing's going to keep starting over every time theta reaches pi. So then I took pi and I divided it up into 4. So pi over 4, pi over 2, 3 pi over 4, pi, etc. And I just went ahead and drew 2 cycles of it, all the way to 2 pi. So we get two full periods from 0 to 2 pi. Okay, so then what happens? As we go from 0 to pi over 4, It goes from, r goes from 0 to 3. There's something saying. Yeah, so that's sweep as it sweeps, as the angle sweeps up to pi over 4, r extends, and so you get this curve. And then what happens from pi over 4 to pi over 2? Back to 0. And you can see the symmetry in the rectangular graph, and so you're going to imagine the same symmetry in the polar graph. It's going to go back to 0 by the time it gets to pi over 2. Okay, now what happens here from pi over 2 to pi? From pi over 2 to pi, it's going to go, the radius is going to go from 0 to -3 and back to 0. So where's that going to graph? If we're between pi over 2 and pi, and our radius, our r values are negative, where's that going to really graph? Fourth quadrant. It's going to go out to -3, and then back from -3 back to 0 when we get to pi. So here, one period of 3 sine 2 theta doesn't complete it. We're gonna, as we keep going, we're gonna get more of the polar graphs. We're gonna need more than one period. So what happens now in the third quadrant? It's just like the first quadrant. Out to 3, back to 0. Out to +3, back to 0. And then the fourth quadrant, our angles in the fourth quadrant, r is, again, r is gonna go from 0 to -3 and back to 0. So that will graph in the second quadrant in negative r territory when the angle is between 3 pi over 2 and 2 pi. Out to -3, back to 0. So this is a 4-petal rose. Okay, questions on that? All right, so let's just, so how many people got it before I started? Did you get it before I started? Okay, so good. So you're gonna have, we need to practice. So I have, as part of a review packet for the final, there's, I think, something like 6 or 8 of these to practice, okay? And so you need lots of practice with this. Don't cheat with your calculator. You're not doing yourself any favors. You've got to think through it. Think through. As the angle is sweeping, the r is changing this way. This is going to create this graph. You just have to practice. So what if we want to know the high point of one petal in terms of like y, meaning the highest y value up here? Right, for a change in theta, right? So we want dy d theta to be 0. For a change in theta, we want the y coordinate not to change any. And so that means we need y as a function of theta. How is y a function of theta? Y equals r sine theta. What is r? 3 sine. So r for this curve is 3 sine 2 theta. So y is going to be 3 sine 2 theta times sine theta, r sine theta. So for this curve, that's the y coordinate on this curve, r sine theta. And now we want dy d theta to be 0. So what do we have? So we have to take the derivative with respect to theta, and how are we going to do that for this one? Product rule, right? So it's going to be derivative of the first times the second plus the first times the derivative of the second. So 3 times cosine 2 theta times 2 sine theta plus 3 sine 2 theta times sine theta. Right, that was the derivative there. I was just checking, you guys. Okay, and if we want the high point, like we said before, we want dy d theta to be 0. And so now we have to use some identities. figure that out. So we remember we had identities for cosine 2 theta back in the day when we were doing integrals. Sine 2 theta, so we got to get all our cosines and sines in terms of the argument just theta. Then we can combine some things, factor some things. But we got some significant algebra to do to solve this. So we need identities and algebra to solve that. And then we're going to get theta equals something in the first quadrant here, something greater than pi over 4 that's going to satisfy this equation. And that will be that theta that will be corresponding to that point where y tops off, right? Where y is the highest. Okay, so you got the Clara project for Friday. Keep getting the help that you need. You can email, come to office hours in the morning. And so what I'm going to do is I'm going to assign, I'll post that review packet if you can start working on those sketches, and then I'll post the web work, and we'll just make the web work due Monday, so you have the weekend. There's a whole polar web work, and you can get started on that too.